this will be a quick run through the topics for exam 3. Not a detailed discussion, but just showing you the topics that you need to focus on, concentrate on. Alright, the first one, chapter 28, it's about sources of magnetic fields. In this chapter, you're looking at magnetic fields produced by a straight conductor, a coil, a solenoid, a toroid. First, field due to a straight conductor is given by the right hand grip rule, with the thumb pointing in the direction of the current and the closed fingers giving the direction of the magnetic field. And at a point r distance away, the strength of the magnetic field B is mu naught times I by 2 pi r. So that is the magnitude of the magnetic field. And if you have two parallel conductors carrying current, then there will be magnetic fields set up by both of them, and one of the current carrying conductors, or rather each of the current carrying conductors, will be kept in the magnetic field produced by the other, and therefore there will be a force acting on each one of them. If the currents are flowing in the same direction, it will be an attractive force, and if the currents are flowing in opposite directions, it will be a repulsive force. The force on one of them and on a length of 1 meter is given by F is equal to mu naught by 2 pi r I1 times I2. Remember that this is the force on each meter of one of the conductors. So it depends on both the currents and the distance between them. And this is how the ampere is defined. So the definition of the ampere, using the formula for force between two parallel conductors, the force on unit length or 1 meter is mu naught by 2 pi I1 I2 by r. And if I1 and I2 both are equal to 1 ampere and r is equal to 1 meter, then when you substitute the value of mu naught as 4 pi times 10 to the negative 7, gets cancelled with 2 pi, and you have 2 times 10 to the negative 7 Newton per meter. So we can define 1 ampere as that current which flows through two parallel straight conductors infinitely long, placed in air or vacuum 1 meter apart, and the force between them is 2 times 10 to the negative 7 Newton per meter. So that's the definition of ampere. A very important law in electricity that simplifies matters is Ampere's law. According to Ampere's law, the integral of B dot dl is equal to mu naught times the current enclosed by the path. So you have a current carrying conductor and you imagine a circular path around it, and if you integrate the dot product of the magnetic field at each point with the small length of the conductor, small length of the loop, you should get mu naught times the current. Now we can use this to find the magnetic fields due to different conductors. Here we can use it to find the magnetic field due to a straight conductor, because in this case you're going to get a circle of circumference 2 pi r, and when you rearrange you get mu naught I by 2 pi r, which is the magnetic field due to a straight conductor. So we could use this law to find the field, as shown here, due to a straight conductor. Now, coaxial cables are used for many types of connections, chiefly antenna connections. And the main advantage of a coaxial cable is that it provides magnetic shielding. And if you look at the physical structure, you see the copper conductor right through the axis, and then you see the insulation over it, and then the copper mesh, and then the outside insulation. Basically, the currents that flow through the copper wire and the copper mesh, they're going to be opposite, and therefore there's shielding of magnetic fields that is produced. Next is the magnetic field due to a solenoid. A solenoid is an extended coil, and it has many number of turns, and we could imagine that the magnetic field is nearly uniform in the center of the long solenoid, and outside the field is weak and almost zero. And the strength of the magnetic field in the center is given by mu naught Ni, but remember that the little n is the number of turns in 1 meter. It's the number of turns in 1 meter. Just remember that. And the magnetic field setup has a pole which is south if the current appears to be clockwise from when looking at that end, and north if the current appears to be counterclockwise when looking at it from the other end. Biot and Savart's law. Now, Biot-Savart's law is useful in finding the magnetic field due to an elemental conductor. So if you have a small conductor, or even if you have a conductor divided into very small parts, and you could use this law to find the magnetic field. For example, if you want to find the magnetic field at P, and you take a little conductor of length dl there, and the angle between the line joining the conductor to the point and the length is theta. The current through the conductor is I, and dB, which is the magnetic field due to that small length, is given by mu naught IDL sine theta by 4 pi r squared. That is Biot-Savart's law. Mu naught times I dl sine theta by 4 pi r squared. I is the current, dl is the length of the conductor, theta, as I explained before, is the angle between the line joining the point to the conductor and the length, and r is the distance between the point and the elemental conductor. Brings us to chapter 29. This is called electromagnetic induction. The basic idea in this chapter is that if the magnetic field associated with a circuit changes, an EMF would be induced in it. And the main law is Faraday's law. According to Faraday's law, the EMF induced is equal to the rate of change of magnetic flux. But before that, magnetic flux is the integral of B dot dA, where the area is taken as a vector now, but remember that the direction of that vector showing the area will be perpendicular to the surface. And by Faraday's law, E is equal to negative d phi b by dt. Actually, the negative comes in due to Lenz's law, according to which the direction of the induced EMF is always opposite to whatever is producing the change in flux. So the direction of the induced EMF opposes the original change in flux. So when you combine Faraday's and Lenz's law, that's when you get E is negative d phi b by dt. If a straight conductor moves in a magnetic field, like an airplane cutting through the Earth's magnetic field, an EMF could be induced between its wings. And as the figure represents, the magnetic field is into the plane of that loop, and the straight conductor, this part of the conductor can be moved. When it moves, the area changes, as you can see. So BdA would be d phi b, and dA is length multiplied by velocity times time, and finally you get EMF in a moving conductor is the product of the strength of the magnetic field, the length of the conductor, and the velocity with which it is moved. Okay, the principle of an electric generator is that a coil rotates in a magnetic field. A coil rotates in a magnetic field. As you can see, this rectangular coil here is rotating in a magnetic field produced by the North and the South Pole. And as it rotates, the flux associated with the coil keeps on changing, and an EMF is induced. This induced EMF is the alternating current or alternating EMF, and is given by NBA, omega sine omega t. NBA is a constant, and it is called the peak value of EMF. So you get E is E naught sine omega t. When you take the RMS value, which is equivalent to the DC value of EMF, you get it as E naught by root 2. So the RMS value is equal to peak value divided by square root 2. Transformers. Transformers are very useful in transmission of electric power, because remember that electric power has to be transmitted in such a way that there is minimum loss of electric power in the form of heat, and this loss is brought about by the resistance of the long cables used to transmit electric power. That is where transformers come in, because the heat loss is given by I squared times the resistance. So if we can keep the current low, then there will be minimum loss. And how do you keep the current low? By stepping up the voltage, because when the voltage goes up, the current goes down in a step-up transformer. And that is the equation that shows you the relation between voltage in the secondary, voltage in the primary, number of turns in the secondary, and number of turns in the primary. A transformer works using the principle of mutual induction. But when you calculate the current, as I told you before, the current is less when the voltage is high, because the electric power is the same. So when you write down the equation for current, notice that it's the other way around. And power loss is I squared divided by the resistance of the cable. Brings us to chapter 30. Mutual inductance. So there is self-inductance and there is also mutual inductance. Mutual inductance is the phenomenon where a current flowing through one coil induces an EMF in a neighboring coil. So now you have M21. That means mutual inductance of coil 2 due to a current flowing in 1. It's given by the number of turns in 2 times the flux linked with 2 due to the current in 1 divided by I1. Or it can also be given as, rather the induced EMF can be given as negative of this mutual inductance. So that's the same M here times di2 by dt. So the rate of change of current determines the induced EMF, which means if the current is not changing, the induced EMF is 0. Now, sometimes we have a solenoid with a secondary winding, like you have a smaller coil wound over the solenoid. Let N1 be the number of turns of the solenoid and N2 the number of turns of the coil. L is the length of the solenoid. In this case, the mutual inductance of such a combination is given by mu naught N1 N2 A by the length. A is the area of cross section of the solenoid. An inductor or a solenoid can actually store electrical energy in the form of a magnetic field. And you got to know how to derive an expression for the energy stored. Energy is the work done, so you integrate the work done. Work is power multiplied by time. That brings us to LI because power is EI. And then on integration you get 1/2 Li squared. L is the inductance. I is the maximum current set up in the inductor. LR circuit, when a current flows through an LR circuit, it takes some time for it to grow and to decay. The decay of current is given by this equation. I is the current at any instant t. I naught is the peak current from which it begins to decay, and tau is the time constant. The equation for growth of current when you just switch on a circuit is slightly different. It's I is equal to I naught 1 minus e raised to minus t by tau. Okay, so that's for the decay, and the right side one is for the growth. And the time constant tau is actually the ratio of inductance to the resistance, which means tau has the unit of seconds. LC oscillations, an inductor stores energy in the form of a magnetic field. A capacitor stores energy in the form of an electric field. So if you connect a pre-charged capacitor with an inductor, there is going to be an oscillation of energy between electric and magnetic, back and forth. Well, the oscillations will die down because of the resistance in the circuit. But if there was no resistance, absolutely, then the oscillations will continue. Actually, this is how electromagnetic waves are thrown off from an antenna. But in this case, the important thing is the frequency. The angular frequency of oscillations, omega, is square root 1 by LC if there is no resistance in the circuit. But if there is a resistance in the circuit, the frequency of oscillations will be slightly smaller, and it's given by square root 1 by LC minus R squared by 4L squared. So that is with resistance, and the equation on top is without resistance. Now, AC circuits can be applied individually to a resistance, to an inductance, and a capacitance, and they behave differently. In a resistance, the applied EMF and the voltage are in phase with each other, and the voltage, according to Ohm's law, is given by the product of current and resistance. But in an inductor, the EMF leads the current. Just remember Eli, E leads the current. In a capacitor, the current leads the EMF. And also, in place of the resistance, now we have the inductive reactance, omega times the inductance, and 1 by omega C, which is the capacitive reactance. So omega L is the inductive reactance, which is similar to the resistance, and capacitive reactance is 1 by omega C. And as I said before, in a resistance, the EMF and current are in phase. In an inductor, the EMF leads current. In a capacitor, current leads EMF. XL, the inductive reactance, is omega times the length, and omega is 2 pi f. XC, similarly, is 1 by omega C, which is 1 by 2 pi fc. So when you put all these three together in series with each other, you get an LCR series circuit in which the impedance, which is a combination of the resistance and the reactance, is given by square root R squared plus XL minus XC whole squared. And the the phase difference between the applied EMF and the current, tan phi, is given by XL minus XC by resistance. At resonance, XL becomes equal to XC, which means the impedance becomes minimum, which is equal to the resistance, and the current becomes maximum. And also tan phi is 0, which means phi is 0. And the resonant frequency is given by 1 by 2 pi square root LC. It is the resonance phenomenon of resonance that's used in tuning a radio or a television. We'll also remember that the power factor in an LCR series circuit, although I didn't write it down, is given by cos phi. Power factor is cos phi. Chapter 31. Electromagnetic waves. In this chapter, you have to remember the Maxwell's equations, the 4 equations. First one, closed integral E dot dA is equal to Q by epsilon naught. This is Gauss's law in electrostatics. And closed integral B dot dA is equal to 0, which is the equivalent in magnetism. It's 0 because there are no monopoles. Whatever magnetic field goes out comes back in. And then you have Faraday's law of electromagnetic induction. And finally, you have Ampere's law with the modification done by Maxwell. Ampere's law is actually mu naught I, closed integral B dot dl is mu naught I, but Maxwell added a new term, which is mu naught epsilon naught d phi E by dt. And this term, epsilon naught d phi E by dt, is called the displacement current. That term is the displacement current. So these are the equations on which Maxwell based his derivations, and finally he derived this equation where the velocity of electromagnetic waves is theoretically 1 by square root mu naught times epsilon naught. And you got to have this concept of electromagnetic waves. Remember that light is just an electromagnetic wave. Get the idea of the electromagnetic spectrum from the lowest wavelength to the highest wavelength, starting out from gamma rays, in fact, gamma rays, X-rays, and you go ultraviolet, visible, infrared, microwaves, and radio waves. Remember that spectrum. And then the most important quantity in electromagnetic waves is the Ponting vector, which is the energy traveling out per second per unit area, represented by vector S and given by 1 by mu naught E cross B. 1 by mu naught E cross B. It may also be written as epsilon naught C E squared, or that's in terms of the electric field, but if you want it in terms of the magnetic field, it could be C B squared over mu naught. Ponting vector. Now, in order to transmit audio or video signals, you need to modulate them. Modulation is the process of mixing the required signal with a high frequency carrier wave produced by an oscillator. And there are 3 types of modulation: amplitude modulation, frequency modulation, and phase modulation. In amplitude modulation, the amplitude of the carrier is changed. You can see the amplitude of the carrier here is changed according to the amplitude of the signal. Now that's the signal on top, that's the carrier, that's the amplitude modulated wave. But in frequency modulation, the frequency of the carrier, this time the carrier is on top, this is the audio signal. You can see that the frequency of the carrier is changed according to the amplitude of the signal. So when the signal is at its maximum, the frequency here is maximum, and so on. So that is frequency modulation. You have to remember the block diagram of a radio transmitter and a radio receiver. What you see here is, first of all, sound is converted into an audio electrical signal using a microphone, and then it is amplified using an audio frequency amplifier, and after that the amplified audio signal is mixed with a high frequency carrier signal produced by an RF oscillator. So the mixing is done here. So the audio signal gets up from here, the high frequency radio wave comes up from here, it's mixed up together, and that's why that's called the mixer. And then again it is further amplified. This time the frequency is radio frequency, so the amplifier is called radio frequency amplifier, and then it's given out into the antenna from where it is transmitted. Remember that this is the simplest block diagram that can be for a radio transmitter. Similarly, you have the block diagram of a radio receiver. Chapter 32, that brings us into optics. Whenever and wherever light is reflected, the two laws of reflection are obeyed. Number one, the angle of incidence is equal to the angle of reflection. And two, the incident ray, the normal, and the reflected ray lie in the same plane. You have to know how to draw images by a plane mirror, and remember that it's going to be a virtual image, upright, same size as the object, and behind the mirror at the same distance as the object is in front of it. When you come to a concave mirror, remember it has a real focus. It is a converging mirror, and therefore its focal length is positive. And it can produce both real and virtual images. Also note that a concave mirror is exactly this, has the same properties as that of a convex lens. So a concave mirror has the same properties as that of a convex lens. Now, for a convex mirror, it is called a diverging mirror, and therefore it has a virtual focus and focal length is negative. It can only produce a virtual image. And it has the same properties as that of a concave lens. Let me also remind you that magnification, when you take the sign of magnification, if it is a real image, magnification is taken as negative, and if it's a virtual image, magnification is taken as positive. The mirror equation and the lens equation are the same, and it's 1 by f is equal to 1 by do plus 1 by di. I can write down the equation for magnification. Magnification is m is equal to hi by ho, or equal to negative di by do. Let me remind you one more time that if the image is real, magnification is negative. And if the image is virtual, then magnification is positive. Refraction, light bends when it passes from one material into another. That's called refraction. And it's governed by Snell's law, according to which n1 sine theta 1 is equal to n2 sine theta 2. It can also be defined as real depth by apparent depth. Refractive index could also be defined as the speed of light in air divided by the speed of light in the material. So those are some of the ideas of refraction. Total internal reflection is a special case where the refracted ray returns into the material from which it is coming, returns or rather is reflected, if two conditions are obeyed. Number one, the ray must be passing from a more optically denser to a less denser material, and two, the angle of incidence should be greater than the critical angle. And this equation here is obtained from Snell's law. N is 1 by sine c, where c is the critical angle. We can calculate the critical angle of water to be 49 degrees and of glass to be 42 degrees. And in that context, diamonds sparkle because they have a high refractive index, and therefore they have a very small critical angle, enabling more rays to be totally internally reflected, which makes it appear as if light is trapped inside, and therefore it makes it appear as if there is a bright source of light inside a properly cut diamond. Lensmaker's equation, we're coming towards the end of this chapter, is 1 by f is equal to n2 by n1 minus 1 times 1 by r1 plus 1 by r2. Note that n2 is the refractive index of the material of the lens. n1 is the refractive index of the material surrounding the lens. R1 and R2 are the two radii of curvatures. And if it's a plano convex or plano concave, the plane surface has a radius which is infinity. Finally, the power of a lens is the reciprocal of its focal length taken in meters. And power is measured in diopters when the focal length is in meters. Well, I have taken some time to do this. Let me finish it off with eye defects. In short sight, the near point, you know that for a normal person the near point is 30 centimeters, but in short sight, in short sight the near point is 30 centimeters, but the far point, instead of being infinity, is something, maybe 70 centimeters. So when you use a concave lens, the concave lens has to produce the image of an object at infinity, at exactly 70 centimeters, so that the eye lens can take it from there. It's corrected using a concave lens. In long sight, the far point is okay, it is at infinity, but the near point is shifted further away. So the near point may be 70 centimeters, but the far point is infinity. It's corrected using a convex lens. So the lens has to produce, when the object is kept at the actual near point, which is supposed to be like 30 centimeters, if you have an object there, the convex lens should take it and produce its image at 70 centimeters. Well, remember, this is just a review. That's why I was going fast, and you've been taught all this. So I hope that you will prepare well for the exam using this. Thank you so much.